Any questions about Project 3? Okay, again, the recitation is available with the video. Please watch the slides and then post on Piazza if you have questions. All right, in terms of database talks, today after this class, we will have CMU DB alumni, Ryan Johnson. He did his PhD here in, I think, 2010, and he won the Jim Gray Best Dissertation Award in Databases for Sigmod. So he's now at Databricks working on Delta Lake. Delta Lake is going to smell a lot like the hoodie stuff and the iceberg stuff and the Duck Lake stuff. So it's sort of in that sort of same space. It was Databricks' version of Iceberg. It didn't get quite the adoption that Iceberg had. So they paid $1 billion for Iceberg, right? As one does if you're Databricks. Tomorrow at noon in the Gates building, we're having somebody give a talk from Uber, talking about the Apache Pinot project they use internally. And sort of talk about the various things they tried throughout the years and why Pinot was the right choice for the problems that they're trying to solve. Again, that one there'll be food. That one's on Gates. And then a week from now, we're having the other database startup that Databricks bought this year called Mooncake. And this is Iceberg, is using DuckDB to connect to Iceberg inside of Postgres. And again, all these are optional. All right, so at this point in the semester, where we're at is that we've gone up the entire stack, right? Like we started off talking about how to read and write things to disk. And your buffer pool manager talks about how to manage memory. Above that, we talked about how to actually access tables that we're storing in our buffer pool and that are based in our disk manager. Then we talked about how to build the query engine to actually execute queries. And then the last two lectures was about how do we take a SQL query from the application, convert that into an optimal plan that we can actually run and execute inside of our system, right? So at this point in the semester, you know how to build sort of a first pass, first implementation of a end-to-end database system, taking SQL queries all the way down to data on disk. But obviously, we're not done yet because we still have a few more weeks left in the semester, right? What we've built so far is a nice database system, but it's not suitable for production because it's not safe, right? We haven't talked about if you crash, how do you make sure you come back and you don't lose data? We haven't talked about if you have two queries trying to update the same thing at the same time, right? How do you make sure that's safe and reliable? So that's where we're going on at this point in the semester for the next 3 weeks. And we're going to talk about concurrency protocols and recovery management, right? And the reason why we don't really show that in this sort of the stack hierarchy that I was showing before at the beginning of the semester is because these concepts and these components are going to overlap and be intertwined with all the parts of the system. So the buffer pool manager you built for project 1 had no notion of transactions, no notion of whether it's safe to write data out to disk. Right? When your eviction policy algorithm ran, you just said, all right, this page is not dirty, I can or I can throw it away, or this page is dirty, I'll write it out to disk. But we'll see as we go along, there's actually another notion of safety we have to be aware of to know when it's actually safe to actually write that data. So if we end up crashing, we don't come back with an invalid database state. We don't come back with corrupted data. Right? What if a tuple touches 2 pages, right, for a single update, and I only write one of them and not the other one? How do I make sure that I don't come back and see a torn write? So that's where we're going next. And so we'll start off with concurrency protocol. That'll be today's class, all this week and a little bit next week. And then next week we'll pick up on, I should take it back. Concurrency control is so important. It's the next 2 weeks. And then after that, we'll do a week of recovery management. Like how do you crash, make sure you come back and everything's still there? I'm just trying to emphasize it. Like, again, these things we're going to start talking about next are all throughout the rest of the system. We're going to sort of go back and revisit some of the things that we've talked about already and say how we then infuse the notion of transactions and correctness inside of them. Okay? All right, so what are we talking about now, right? So we've been talking about these SQL queries so far in the semester, and we're really sort of focusing on doing sort of not so much simple things, but the scope of the data that they're accessing or modifying is sort of limited to like one query. Like, yeah, I can do joins or subqueries in a single query, but really when it comes time to like updating things and modifying things, we've been focusing on sort of really simple operations, like one operation at a time. So now we need to expand our discussion and our vernacular to understand what it means to start doing more complex things inside of our database system. So here's a typical sort of application somebody might want to build for like a bank, right? Where I keep track of like how much money somebody has in their account. And so on the other side here, where I'm showing this is the application code that someone would write to build a bank application against a database, right? Whether it's in Python, PHP, Java, Rust, it doesn't matter. Like the high level concepts are what we care about. So say I want to do a bank transfer, right? And so I'm going to access object A, read object A. So that's somebody's bank account. And I'm first going to read how much money I have in that account. So the application will get back now the balance at $100. Then if I'm going to transfer $25, I got to make sure that this account has sufficient funds to do that transfer. So I'll have a client-side check that says, does this account have $25? If yes, then I'll go ahead and do the payment to some other account, like think Venmo, Cash App, whatever, doesn't matter. Right? I'm going to pay $25 to somebody other account, but then now I need to deduct $25 from account A, right? To take the $25 out, and then now I have this new balance of $75. I want to write this back now to the database system to now reflect that I've transferred $25 out of this account and sent it to somebody else, right? Pretty straightforward. So the question we're going to try to deal with today is, what happens if the database system crashes before I update the balance? So I've sent the $25, put it in another account, and then now I crash. When I come back, what should be in the bank account? Right, my account, and then also whoever I paid, how much should be in their account? Right? Another example is to say run the same sort of application code again, but this time, for whatever reason, you and your best friend, your roommate, share bank accounts, and you both want to pay somebody $25 at the exact same time. So on the website, on the system, in the application side, you're going to run the exact same code, but it's going to run at exactly the same time. So you're going to have sort of two threads or two instances of this application logic running at the same time, either on the same machine, different machine, it doesn't matter, right? Because the database is keeping track of how much money is there. So they're going to do all the same steps. Go get the current balance. We have $100. Check to see that at least we have $25 to send it. Yes, we do. Then go ahead and pay that $25. Now update the bank account with the new balance, $75, and then now try to write this new balance back to the database system. And obviously this would be bad because if we allow this to happen, whatever, they're both trying to update with $75, but they both sent out $25. So the real account balance should be $50. But if I let them overwrite each other, then I'm ending up with incorrect state of the database. Right? This is talking about concurrent access. So there are two main issues we care about. If we crash and come back, how to make sure that the state of the database is what we expect to see, and then how do we handle two or more transactions trying to update the same thing at the same time. And so this is what we focus on today when we talk about concurrency protocols. It's the mechanisms the database system is going to implement to prevent all these problems from occurring. All right, so let's think of a really easy system we could use to solve this, right? Say that we have in our database system, we only have one worker that can only execute one query or one transaction at a time. Let's say one transaction. So that means that when the application sends requests, even though there may be multiple requests, it's only going to execute one of them at a time. Think of a single queue. And then now, when a transaction begins to start updating the database, instead of overwriting existing data that we have in our pages, we're instead going to make copy of those pages. Think of, again, slotted page architecture, making copy of those pages. And then we're going to apply all our updates to those pages. And then when it comes time to commit, we then just flip some internal mechanism, like the page directory, to say, here's the new version, the latest information about those tuples. If the transaction fails or we crash, then when we come back and those pages that were from the uncommitted transaction, we just ignore them and clean them up. So is this proposal correct? Will this guarantee that I don't have the two problems I had before, where if I crash halfway through the transaction, I end up with invalid database state? And does this also prevent me from having two or more transactions, updating the same record at the same time? Yes, what? Yes, it is correct. Is it safe?
Well, except for like when you write the little part when you write to disk, I don't know if there could be an issue there. Like the section where like you're happy with your new copy and you go write it.
A statement is when a transaction commits, that's the happy part. when you're happy that you made your changes and you go ahead and commit, you're saying there's a small sort of small window where you may not be able to flip over that and say you successfully completed the transaction.
Well, like if you're currently writing to this thing, then now it breaks like while you're writing.
When we say when you're currently writing this, we made a copy of it, right? So we're updating the copy, not the original.
Yeah, but you have to save your copy back onto the original.
The statement is you have to save the copy on the back of the original. What if we instead just update a single page that says, here's the latest version of those pages? And we can do that atomically. Okay, it works meaning it's safe and correct. Who agrees with that it's safe? Okay, who agrees that it's correct? All right, for those who don't think it's safe or correct, do you think it's not safe or correct, or you just don't know? It's okay to not know. Who here says this is a terrible, sorry, who says this is not correct and or not safe? Okay, well, you're all correct. This is correct and safe. Do we think it's performant? No. Why?
Because you copy everything.
Well, yeah, so in this case here, yes, we're copying the entire database. You could be more fine-grained, say, if I only update 2 pages, I'll update those 2 pages, right? You could do that. You said you don't have concurrency. Correct, yes. That in this world, you can only allow one transaction to update the database at a time because there's that little piece at the end where you flip and say, here's the new pages. That needs to be done atomically, and I can only allow one transaction to do that at a time. So yes, so this technique here is called shadow paging, and we'll cover it in more detail. This is basically what IBM did, or not basically, it is what IBM invented in the 1970s when they invented the early concept of transactions. Like Jim Gray, the guy we talked about before, he won the Turing Award in the 90s for all of this transactional stuff that we'll talk about here. This is what they did in the 70s. They abandoned it later on because of its performance reasons, which we'll cover in more detail in the next 2 classes or so. But this would work. This is kind of what SQLite does too. If you switch on, they have a special mode you can switch to shadow paging. They'll basically do this, right? But as we said, like if you only allow one transaction to run at the same time, then you're sort of not getting the full parallelism you want to have in your database system. So what we really want to do, and what the next couple lectures are trying to solve, is how do we allow for multiple transactions to run at the same time simultaneously and interact with the database, either reading or writing with it at the same time. I mean, it's sort of obvious why we want to do this. We want to take advantage of all the additional parallelism we have in modern hardware, like more CPU cores. We'll eventually, we're talking about single node systems now, but we'll talk about distributed databases in a second. Same idea applies. If I want to go across multiple nodes, that'll get me better parallelism, better scalability. And it'll appear to the end users that the data system is more responsive because I'm not submitting a transaction then waiting, maybe a second for whatever transaction that was queued up in front of me to finish. I may have to still do that in some cases, and I may end up aborting if I try to write something that somebody else has already wrote to. But we'll cover what that means in a second. But in general, this allows to get the better performance for in our system because we're taking more advantage of the hardware that's available to us. But as I was sort of saying before, it's great to be fast, but we also want to be correct. And actually, in database systems, usually you want to care about correctness first and then performance later. Because it's oftentimes very hard to build a fast system and then go try to make it correct later on. You're better off building a correct system first and then figuring out how to optimize it without relaxing those correctness guarantees. And this is super hard. There was a bug found in Postgres' implementation of this probably 2 or 3 years ago. Postgres has been around since the 80s, or since before most of you guys were born. And they're still finding errors in these protocols. So it's super hard to do. Fairness, we'll talk about a little bit when we talk about two-phase locking next class. But this is giving making sure that no one transaction or no one application is starved out indefinitely if you're trying to get access to the data. But again, we'll cover that when we talk about how to break deadlocks next class. All right, so what we're trying to do here is we're trying to allow for an arbitrary interleaving of operations against the database, so read and write operations. But during this process, while a transaction is running, there may be moments in time where the database is actually inconsistent. It means that the database is actually incorrect because you kind of have to apply some changes, right? But that's okay as long as those inconsistencies don't persist after a transaction commits or after a transaction is aborted because of restart. Right? Those things are bad. That's what we're trying to avoid. But during transaction execution, like going back to my example here, right? When I took $25 out of this bank account, ignoring the running in parallel, and then before I sent $25 to somebody else, and then before I took out the $25 in my account, there's technically an extra $25 floating around in the system. Right? We're talking nanoseconds here, potentially. But in that case here, it's incorrect, because there's $25 more than it actually should be. But that's okay, right? Because we have to do that because we can't just do magically, apply changes atomically in one instruction at the level we're talking about here. So that's what I mean by the temporary stuff. It's okay, but we have to make sure we don't let things persist forever. The other important thing to understand too when we talk about transactions here is that we only care about, we being the database system, we only care about what's in our purview of control in our database system. So what I mean by that is we can only handle the read and write operations on data that we manage, that we have control over. If the application does other stuff, like send a confirmation email or like launch a missile in the middle of a transaction, and then our transaction aborts and needs to roll back, we can't roll back that email, roll back that missile, right? Because the data system, not yet at least, doesn't control everything in the world. So anything outside the scope of a transaction, the read and write operations we're talking about in the data that we manage, right? We can't revert those things. So there may be inconsistencies in the real world, but the data system doesn't know about it, doesn't care about it. Okay? All right, so in order to understand this, we got to start defining what we mean by database and objects and what these transactions are actually doing. So for today's class, we're going to simplify the problem and not talk about tuples or pages or indexes or rows, anything like that. We're only going to deal with abstract objects. We'll give them names A, B, C, D. It could be a tuple, could be a table, could be a database. It doesn't matter. All the protocol stuff we'll talk about here today and going forward will still work in this, with this sort of this sort of abstract notation. The other important thing to understand is that we're going to assume for this class, today's lecture, that the database is going to be fixed size, meaning all the objects that we care about, A, B, C, D, whatever, they're going to exist before transaction starts, and they're still going to exist after the transaction starts. And we're not worried about inserts. We're not worried about deletes. Those complicate things, and we'll have to handle that next class. Today's class, we just assume that these objects are always there. We can update them, we can read them, but we can't delete or insert new ones. So now we're going to define transactions as a sequence of read and write operations on these database objects. So I can read A or I can write A. And we'll define that when a transaction starts, when it invokes begin, right? That's in the SQL syntax. I think sometimes some systems might support start, but begin's usually what people use. And then we'll say that a transaction finishes either when they call commit or rollback or abort. Right? Rollback and abort are the same thing. That I know you can do in SQL for either one. Commit means like save all my changes, apply them to the database, and rollback says undo any writes that I've done and make it as if I didn't do anything. Okay? So the notion of correctness we're going to have for our transactions are going to be defined by the acronym ACID. Who here has heard ACID before? All right, almost half, perfect. So now we're going to go in more detail what each of these are. So ACID stands for atomicity, consistency, isolation, and durability, right? And in full disclosure, atomicity and isolation and durability, these will be easy for us to understand today. We're going to focus mostly on isolation. Consistency is kind of a weird one. It'll make more sense when we talk about distributed systems, but we'll cover it as we go along. So atomicity just means that for a given transaction, all the operations that a transaction invokes or executes, either they're all going to occur or none of them are going to occur. So I can't have any partial transactions, right? So you can think of it as like simplify, it's all or nothing. Consistency means that it has to do with like correctness. So like if the database is currently consistent or correct, and my transaction only does consistent things, then when a transaction commits, my database is guaranteed to be consistent. That doesn't mean anything, like probably doesn't mean anything to you guys either, right? Again, when it's a single node system, it's kind of hard to discuss, but like with distributed system, another way to think about this is, if I write to a data object A on this node here, and I go to commit, I can immediately reflect those changes on all other copies of the data on other nodes. Immediately. They say it's physically impossible. No, depends on who's tracking. Again, we'll cover that later. All right, isolation is the idea that a transaction is going to execute as if it has the complete access or is the only transaction executing at that given time on the database system, meaning it can't see writes from other transactions at the same time, because you wouldn't see that if you were truly isolated. And the last one, durability, just means that if my transaction commits, then I'm guaranteed that my changes will survive no matter whether like the machine catches on fire or another, the system crashes, the OS crashes, right? Obviously, if the machine catches on fire and your disk melt, like then you potentially don't get anything. But the way you handle that is replication. Now you're talking about distributed systems, and then again, we'll cover that later, right? I'm being hand-waving. I've been trying to like do baby steps into this to understand how we're actually going to do this on a single node, and then we'll expand it on a multi-node system. So again, atomicity, isolation, durability, pretty easy to understand. The German guy in the 1980s that sort of coined this moniker, acid, right? He kind of shoehorned consistency in there because like he was trying to just make it sound nice, like acid rather than aid. And then he was trying to make a joke against his wife. This is the story goes. I've never met the guy, so I don't know. That his wife didn't like sugar and sweets, so he called her an acid woman. So that's why he had to get the C in there to make it all work, right? But again, we won't talk about much today's class or when we talk about the Concurrency protocols, but it'll make more sense when we talk about distributed systems. All right, so today's class, we're going to go through each of these concepts one by one. Again, we'll focus mostly on isolation because that's going to be the most important concept in all of this. All right, so for the case of atomicity transactions, as I said before, we don't want to allow partial transactions. So there's only two possible outcomes when an application starts a transaction in our database system. It's either going to commit and have all its changes apply to the database, or it's going to abort and roll back and have all its changes reversed. So as if it didn't even execute at all. And one important concept that we'll focus more on next class is this rollback process could either be initiated by the application itself, like the application can say, I don't like what I'm doing, abort my transaction, or the database system can say, I don't like what you're doing, I'm going to make you stop and abort your transaction and roll you back. And in your application code, which is again outside the database system, your application code has to be able to handle that. So if you start a transaction in your application, you have to catch the exception that you may get aborted, and it's up to you for you to decide whether you want to retry it or not. But the question is, can a single query abort? Sure, why not? Yeah. Let me think about that's true or not. Yeah, you could say, now we're getting the weeds. So it depends on the Concurrency protocol. You could have it like try to update something that another transaction tries to update at the same time, and then therefore you block and wait, and then you might time out and get aborted. Right? We can do examples of that, and then it depends on the isolation level. We'll cover that next class. Right? It gets complicated, but in general, yeah, it could. A single statement transaction is still a transaction. The statement is implicitly every query is a transaction. Yes. So when you open up Postgres today and you write a query, it's going to technically runs begin and commit around it, even though it runs that one query. Yes. It's called auto commit. You can turn that off so you can do update, and without calling begin, and it creates a new transaction. But you still have to call commit or rollback at the end. I must admit, I love transactions. They're like super awesome. They're super hard. So I get excited. That's why I'm like riffing on everything he's asking about, because like we can give demos and it's all awesome. It's great, and it's really hard too, even though it's an old topic. Okay, so again, so I said the database system guarantees to the application server that your transaction will be atomic. So either everything's going to execute or nothing's going to execute. So there's two high-level ways we're going to be able to provide this guarantee. The first is going to be through logging. And this is the most common approach that most systems use. And it's challenging because the term log has a bunch of different technical name or usage in data systems, right? You think of like a debug log, just printing out printf statements. We saw this before with like log structure merge tree. It's kind of the same idea, but it's basically just a record in a ledger of an ordering of here's all the operations that a transaction made or applied to the database system. And we can either store this as in a separate file, like a Red Hat log file, which we'll cover in a few weeks, or we can actually just have the database itself be like the log structure merge tree, like have that be the log we're using to figure out what transactions actually did. So in this log, we can keep track of all the actions that occurred and also redo information and undo information. So undo information would be like how to reverse the change that they applied, and the redo would be how to reapply the change. And we're actually going to end up needing both of them. And we'll have to maintain this undo log in memory as transactions are making changes. And then we'll see this in a few weeks, but in our bufferable manager, we're going to have to make sure that when we flush out a dirty page that's been modified by transaction, we got to make sure the log record that corresponds to whatever that made that page dirty, that's got to be get written to disk first before the page that got modified gets written to disk. And that simple ordering is going to guarantee that we can crash and come back and restore this to the database correctly. Right? There's those flight recorders or black boxes in airplanes that keeps track of like, here's all the things that are occurring in my system right before the crash. And they've recovered that to figure out why the plane failed. Same thing in our database system. It's the black box recorder that keeps track of. Here's all the changes that are occurring. Some of them are written to disk, some might be in memory, but at least when we crash and come back, we can look inside that and figure out what was going on to put the database back in the correct state. Yes?
So the thing logging, are we really logging the action itself, or are we logging like each individual snapshot of the action?
The question is, what are we logging?
Yeah.
And the choices are, am I recording like a snapshot of the record, like the tuple itself, or am I recording like what was the change? Yeah. It depends on how you implement it. The answer is both. You could do both.
Operation is like something like aggregation. After aggregation, we already lost the initial granularity. How can we roll?
So his question is, if I'm recording the aggregation, like as an update query, or
after the aggregation, we already lost granularity or original information. How can we undo the operation?
The statement is, if I say I do a select query, get an aggregation, and then I update some other record with the corresponding aggregation, so the log will be ordered such that when you recover it, you can go back to the previous state of the database and replay that transaction. And I actually don't care about I don't care about the aggregation. I only care about what's the final computation that I put in the database. As long as that occurs in the same order the first time it ran, then I'm okay. So that's getting ahead of ourselves. That's called physiological logging, where I'm recording the actual changes, like the byte level changes, like a diff and get. You can do logical logging, where it's actually the query itself gets logged, and then you re-execute the query. So if the query took an hour to run the first time, when you recover the log, it takes an hour to run again. But sometimes that's okay, because if I'm doing real fast things, it's actually faster for me. So like we'll get to that in like 3 weeks, but like the answer is yes. This thing is being ordered and with all the changes that are getting made, so that if I crash and come back, I just replay the exact same order, and I am guaranteed to get back in the correct database state. All right, so we want to do this for efficiency reasons in some cases, because it'll be faster for us to write a sequential log out to disk rather than random I/O for pages. That's the same argument we saw with the log structure merge tree architecture versus like the heap files or the slotted pages. But again, sometimes people also keep these logs around forever, or at least 7 years. Like if you're a financial firm, you got to keep track of every transaction that everyone's ever made for 7 years if you ever get audited by the regulators. And so this log information can be used for that as well. The question is, again, it's related to his question. What am I recording my log? Is it the actual operations I did, or like the byte level changes? It depends. For undo you'd have to record what the previous value was, because if it's like if you're recording like update value +1, I have to know what the previous value was. Again, like depending on how you're replaying the log, you may need that previous value, may not. We're getting way ahead of ourselves, but snapshots is the way to handle your problem. If you don't have the undo, just go back to the previous version and replay in the same order. Again, getting way ahead of ourselves. But you guys are you're understanding like this thing can be replayed, so we can put the days back in the same state. The other technique is what we already talked about at the beginning, the shadow paging. Again, this is where you make copies of pages to allow the transactions to make those, update those copies instead of the original versions. And then when they go commit, you just flip pointers and say, here's now the latest version of the pages. Yes, in the back. Yes. That the right-hand log will be expensive? You said? All right, so our statement is, can I briefly discuss like what's the performance of these two approaches? And there's two notions of performance. There is normal operations when I'm running transactions, and then there's if I crash and recover, how long does that take? Most people, most places care about the normal operations. You say, oh, my database is not going to crash that often, so I want to run as fast as I can. And then, yeah, if I crash, then I'll pay that penalty. So the write-ahead log approach is actually faster at runtime for normal operations because I can just append to a log and write that out sequentially, right? Now, when I crash, come back, depending on when I'm storing my log, I got to replay it, and that could take hours potentially. Worst case scenario, days, right? Where in the case of shadow paging, it's going to be slower at runtime because I got to make a copy of the page and then apply my changes and then somehow update up some pointer to that point to the new pages. But when I crash, come back, it's super fast because I just ignore all my shadow pages because those transactions didn't commit, and I come back and my database is instantly in the correct state. So again, most systems are going to care about their normal operations and choose a write-ahead log approach. There was one system in the 1970s, I forget the name of it. It was actually built by the Puerto Rican power company. And it was like, I don't know, the 70s in Puerto Rico, the infrastructure was not that great, although it's not much better now, but still. So they had a database system. They were sort of keeping track of like the usage of various customers. And because they were having all these power outages, that they chose a shadow paging approach because 3 times of the day the power would go out, the database would crash, and you don't want to spend an hour waiting for the system to come back online, the database to come back online after a power outage because it might crash again. So they chose shadow paging because when they would crash, which is unpredictable, when they came back, they could have the database instantly available. So they were choosing slower runtime performance in exchange for faster recovery. But most people are going to choose the opposite. So the very few systems do this today. Again, IBM did this in System R in the 1970s, but when they built DB2, they switched to the write-ahead log, the previous slide. Probably one of the most famous ones doing this is LMDB. And he's the opposite of me. Like he loves mmap and he loves shadow paging, and that's what he uses. I think CouchDB still does this. There was an early key value store called Tokyo Cabinet from 10 years ago that was doing this. But in general, like I guess as we said many times semester, you don't want to do this. Write-ahead logging is always going to be superior choice. And there's tricks to make the recovery actually go faster. Depends on how much you want to take snapshots and so forth. Right? Like in general, the write-ahead logging is going to be the superior approach. Yes, and yes, I'm leaking ideas coming ahead. Yes, I should just say logging, but in actuality, you call this write-ahead log. So the idea is you're writing the changes you make to the database to the log first, then you update the actual database itself. That's the write-ahead logging. Yes.
What happens when you wrote the log and before you did the changes it crashed?
The question is, what happens if you write to the log, that gets written to disk, and then before the changes to the actual data gets well, if you crash and come back, you replay the log and you come back. And you
well, what if you want to roll back and then
you can't roll back. If you say commit, all right, so there's another notion too we gotta understand. So if my application tells my data system I want to go commit, I may crash before I get the acknowledgement that my transaction committed. And that's okay. So meaning like you tell me to commit, I commit your transaction, and then now I'm about to send you a message, hey, I got it, good job, right? But then I crash before you get that message, that transaction is still committed. And it's your job to go figure out whether it actually committed or not. We can't, the database system, and that's still correct, right?
So it only starts writing the log after you tell it to commit.
We're getting ahead of ourselves. Some systems will keep everything in memory. Some systems will actually write things to log. You want to write things, write the log out to disk. You want to write it out to disk because that means if I need to update 1 billion pages, but I only can keep 100 in memory, then the write-ahead log is how I'm going to be able to handle that. If I have to keep everything in memory, then I can't keep everything in memory. So it's okay for me to write the log out to disk before I finish or transaction commits. But as soon as I'm told commit, and as soon as on disk it lands a commit message in the log, that transaction is committed.
Okay, but then it's possible that like in the middle of a transaction, you start writing logs.
Yes.
To disk.
Yes.
And then before you actually did the changes to the data, it crashed.
Yeah.
And then you came back up, and you don't know like if those logs are actually written to the actual.
No. So the statement is, it may be the case where my transaction is updating the database, and I'm writing to this log, and some of those log records are getting written to disk, and you haven't told me to commit yet, right? So I haven't. The application hasn't told me to commit, and then I crash. Correct. The log can help us do that.
But like the log has data that you didn't actually write.
All right. So there's the log, and then there's the data. The log tells me what I was trying to do to the data. So when I crash and come back, I go look in the data and say, did I actually make those changes? Yes or no. And if I did, and they shouldn't be there, I have to roll them back. Yeah. This gets very hard. It's very complicated. The answer is yes. We'll spend one whole lecture on exactly that problem. Yes, because then you got to worry about like my log grows forever, right? I don't want to run my database for 5 years and then crash and have to replay the log for 5 years. So what do? You take checkpoints or snapshots so I can truncate how far back in the log I got to go. But what happens if I have a transaction started? I take a checkpoint and then the transaction finishes, and now it spans checkpoints. How do I handle that? The statement is, again, we're getting ahead of ourselves. The statement is, and I like this, the statement is, well, just don't take checkpoints while transactions are running. My checkpoint takes, say, half an hour. Do you want my website to be down for half an hour? No. Right? And in the financial world, those guys are paranoid. They take checkpoints every 5 minutes. So we'll talk about how do you allow transactions to keep running while I'm taking checkpoints. They're called fuzzy checkpoints. It's hard. It's awesome. Yeah. And there's this book, or sorry, not a book. We'll spend a whole class on the algorithm is called Aries. It's developed by IBM in the early 90s. It's 75 pages. It's like that's the Bible on how to make sure your database is fail-safe on a single node. Again, if the machine catches on fire, you're screwed there. Then you use Paxos or Raft, whatever, to span things out across multiple nodes. We'll get there. Okay, don't do the shadow benching. All right. Consistency, this thing, right? So again, we're trying to say our database is trying to model the real world. So we want to make sure that we don't allow for transactions. We don't allow transactions to make changes that would violate, parameters or aspects of the real world. So for example, if I have a database of keeping track of everyone's age, like it's a single integer, nobody can be a negative age, right? So I want my database system to not allow that. And therefore, if a transaction tries to update someone's age record to say now they're negative 100 years old, the data system should not allow that, because that would be an inconsistent state of the database, right? So this is not something the data system can do for you automatically. It doesn't know what it means for someone to be a negative age, or it's just storing integers. So these constraints are things that the application has to tell us, either through like the add constraints, or like when you create the table, you can call it check. Not null is another obvious one, right? So these are all, it has to be told these constraints ahead of time, and the data system, if it wants to be consistent, has to enforce them to make sure that no transaction actually can update the database in an invalid way, right? So you may have heard the term eventual consistency, right? This is when we're getting ahead of ourselves a little bit, but this is when we start talking about multiple nodes, like distributed systems. So eventual consistency means that if I have a copy of the data that's replicated on, say, 2 machines, and so when my transaction modifies something on one machine and I commit, that change should be immediately reflected on the other machine if I want to have consistency guarantees. So that means if I commit here and I immediately try to read that same record on another machine, I should see my own write. Eventual consistency basically says, well, this is hard to do, so we'll have 2 copies of the data on 2 machines, And when I update the one machine here, I'll eventually update the other one. So there's a window, a small window where I may do a commit on this node, then go try to read that same record on another node, and my change hasn't been propagated yet. So therefore, I see the older version, right? This is what people did in the, this was the hot thing out of Google in the 2000s. But we'll talk about this in the class. Like, they basically said, oh, that was actually a mistake because now you have a bunch of JavaScript programmers trying to reason about inconsistent, incorrect data, and that's never good, right? So most of the modern transactional systems don't do this. We'll cover this briefly and see how to not do it later in the semester, in lecture 23. What is what? Integrity constraint, sorry. Right, like not null is an integrity constraint. Check that no age is greater, no age is less than 0. Right, those are integrity constraints. Thank you, I should update that. All right, so the main one I want to talk about is isolation of transactions. And again, this means that when application submits queries, submits transactions to the database system, they're going to assume that they're running by themselves. So they're not going to see weird intermediate states from other transactions that might have found in the database, right? It's going to be as if it's running in serial order. And this is a good thing because this is a way easier programming model for your random application developer to reason about, right? Think of like JavaScript programmers, right? Like, you don't want them to start thinking about, okay, what if I update this and another guy updates the same thing at the same time? How do I handle this? If you just assume I'm going to run in serial order, then you don't, it's as if you're running on a box by yourself, right? But as we already said, we want to be able to interleave these operations from these transactions at the same time so that, we get the better parallelism and get the better performance. But we still need to make sure that they're going to run as if they were running one at a time, even though they're not. So this is what the Concurrency protocol is going to provide for us. In addition to the logging and all the other stuff, it's sort of the whole big picture. But this is basically the coordination mechanism inside of our database system that we're going to use to figure out what transaction can run at what time, what data are they allowed to read and write, and then when they go to commit, are they allowed to do that or not? Right? There's other things like we'll talk about next class, like how to handle deadlocks or either breaking them when they occur or prevent them from occurring. That's next class, right? Well, in general, there's going to be basically two approaches to this, right? Which I just sort of said, right? There's going to be pessimistic and optimistic concurrency protocols. Pessimistic says that I'm assuming you're going to have conflicts with other transactions, so I'm going to prevent you from doing certain things to avoid these conflicts, right? Trying to stop you from doing something wrong ahead of time. Optimistic assumes that the conflicts are rare, meaning two transactions trying to read and write to the data at the same data at the same time. So I'm going to allow you to do whatever you want, but then when you go to commit, I'll go figure out what you actually did and go to clean things up. All right. So let's look at an example here of how can you allow this interleaving and what it means. What does it mean for things to be correct? A correct interleaving. So again, we're doing same bank application. We have two accounts, A and B, and each one has $1,000 in it. So transaction T1 wants to take $100 out of A's account and put it into B's account, and at the same time, we have another transaction T2 that wants to compute 6% interest on the accounts and give them a bump in the money, right? So we want to see how can we interleave these transactions at the same time to again, improve the performance of the system, reduce the total amount of time it takes to execute them. So the first thing we understand is what are the possible outcomes we could have for interleaving these two transactions here, right? The answer is a bunch, right? I mean, they're not doing that much. There's only two transactions. There's only two objects, so it's not it's not infinite, right? But for this application, the thing we care about at the end is that there's no money missing and there's no extra money that shouldn't be there. So an easy way to think about it is if I just take the two accounts, they both have $1,000, so I end up add them together, I get $2,000, and then I compute 1% interest on them, or 6% interest on them. The final state of the database, the total amount of money I should have in my database should be 2120. So an important thing to understand in this world of database systems, at least what we're talking about here today, that it doesn't matter whether T1 is submitted first by the application and then T2. We're allowed to execute them in any order that we want. So the order of their arrival on the box doesn't matter. We can still order them, in any way we want to try to get the best performance. If you care about those things, that's called strict consistency or external consistency. Very few systems support that. Google Spanner is probably the most famous one. That Google Spanner will guarantee that if one application submits T1, and then like a half a millisecond later, another application submits T2, it'll guarantee that T1 commits before T2. To simplify our problem today, we're not going to guarantee that. We can still reorder them. But the outcome, again, we want, in order to make sure that we have this 2120 number at the end, is that whatever interleaving we come up with, we want to be as if they executed in serial order, meaning one after another. So that means that there's only two database states. Either I run T1 first followed by T2, or I run T2 followed by T1, right? And I may end up with different values for the accounts from A and B. But again, if I just add the total amount for each of them after the transaction is committed, I still end up with 2120. So either one is correct, no matter how the transactions are submitted by the application. And that's a different notion than maybe thinking about correctness if you're running on like a single node parallel system, like strict memory orderings, right? In this case here, the data system is given freedom to reorder this anyway at once, as long as it appears as if the transactions executed one after another, right? So again, the two possible serial orderings are T1 executes followed by T2, or T2 executes first followed by T1. And again, if I just look at the final outcome of the state of objects A and B, when I add them together, it's always going to be 2120. The question is what? Sorry, again?
Why did we arrive at the variant that the sum should be constant and nothing else? Is it because of the nature of the operations you're running, or like how would the system determine this algorithmically?
The question is, how would I determine this algorithmically? So that'll be the concurrency protocol, right? So today's class, we're going to talk about like just identifying whether the ordering is correct or not. Next class will be how do we enforce that? How do we make sure that doesn't happen? So again, for this class, we're assuming that we're given the queries ahead of time. Sorry, the operations ahead of time. And we know, so we have the schedule ahead of time. So we're not worried about a transaction T3 showing up in this example here. In the back, yes. The question is, wouldn't there exist some kind of requirement or criteria that would be the same across all sequential orderings? Yes. So her point is that I'm showing this example here that I'm saying A plus B equals 2120. And I'm saying we're using that to determine is the ordering correct. I'm just using that as an illustration in this example, right? The things you would sort of really care about is like the values in the objects themselves, right? And then we'll see that when we look at what the operations are actually doing inside the database system, that's how we're going to end up determining whether the ordering is correct or not. For illustration purposes, I'm saying, so to make it more intuitive, A plus B equals 2120, and you can see for the two serial orderings, you always end up with that, right? Yeah, that notion of the higher level notion of correctness, no one, you can't assume someone's going to give you that. Yes.
So the point here is to have each transaction so that, or execute each transaction such that you always have consistency of that criteria, meeting that criteria no matter how you execute it serially, or come up with a criteria so that you have consistency.
Maybe just rephrase what you're saying. Basically what I'm trying to say is that I want to interleave these operations and these transactions, and I want the end state of the database to be equivalent to some serial ordering of those transactions. But there may be multiple serial orderings, and I actually don't care which one I end up with, as long as there's at least one of them.
So what would be a system that is not isolation compatible database, and what is a state where it is isolation?
Let me walk through some examples. The question is going to be like, what's an example of a system that can't guarantee these things? A lot of them. So let me go through serializability and then, all right. But I'll say straight up, like when we talk about isolation levels, you say basically, I want to guarantee, for example, my transactions end up equivalent to a serial ordering. some systems will lie to you and say, yeah, I'll do that for you, when they actually don't do it. Oracle does this. Oracle will say, I want my transaction to be serializable. You actually get a lower level than serializable, right? And in Postgres, theirs was broken for a few years, and someone fixed it 2 or 3 years ago. This is super hard. All right. So let's look at interleaving, a good example. So why would an interleaving occur? Again, so say like, the transaction tries to go fetch, get data in a page, and it's not in your buffer pool. You got to stall that transaction while you go to the disk and go get it. And meanwhile, the database can decide, I'm going to let something else run. So let's say T1 starts, it takes the $100 out of A, and then it stalls because they have to go to disk. And then T2 is allowed to start. It computes the interest on A, but then it stalls because it's waiting for something too, say the same page to read B. So then T1 can start again, puts the $100 back in B, then commits, and then T2 starts running and then can compute the interest on B, right? So in this case here, even though I'm interleaving T1 and T2, it's equivalent to a serial ordering of T1 followed by T2, right? And the key thing to point out is like the operations on A and B are always happening on T1 first before T2, right? And again, just using this as a simple illustrative trick, you end up with the same state. A bad interleaving would look like this, where T1 starts, it gets paused or stalled for whatever reason. T2 starts. All right, so T1 takes $100 at A. T2 then computes the interest on A, then computes the interest on B, and then commits, and then T1 goes and adds the $100 back to B, right? So when we look at the sum total value of the two accounts, we're missing $6 because we computed interest on A while this $100 was taken out of A, but before it was put in B, right? So this is what we're trying to avoid. We're trying to avoid ending up with a state of the database for our objects it's not equivalent to any serial ordering. And again, for two transactions, it's either T1, T2 or T2, T1. But think of like if I have 1 million transactions, how would I come up with that ordering? Right? So as humans, again, just in examples here, I'm just showing like A equals A minus 100, right? I'm just showing this. It's pretty easy for us to understand what's actually going on. This is actually not what the database sees. The database sees this instead. Again, we said all we have are read and write operations on single objects. The database doesn't know, again, the high level meaning of what you're trying to do. It just knows whether you're trying to read or write to an object. So again, in this example here, it's pretty easy for us to look at it and say, okay, well, this is bad, right? And then I compute the sum and I see that I'm off. But how can we actually do this for real? And so we wanted to determine that we have a correct ordering or schedule for our transactions if we can prove that it's equivalent to one of those serial orderings that might exist. All right, so what does it mean to be equivalent? What's a serial order or serial schedule? So the serial schedule we already talked about just means that the transactions are executing one after another, right? And then we're going to say that two schedules of these transactions are equivalent if the end state of the database is going to be the same as if it was executed by the other schedule. So I can take any arbitrary interleaving of a transaction, of the transactions, and then come up with another arbitrary interleaving of the transactions. And if the end state of the database is the same, then we say those two schedules are equivalent, even though the interleaving might be different. And then now I've already said this before, again, leaking terms ahead of time, but we're going to say that this notion that a schedule is serializable if that it is doing an interleaving, but the outcome of the database is equivalent to some serial ordering of those transactions, right? So this is not as intuitive maybe as you understand computing and transactions in other areas, right? But the reason why we're going to allow this interleaving to occur, and we only care about is it equivalent to any possible ordering or serial ordering, is that it gives the database more freedom to identify more opportunities for parallelism to get better performance. If I can only execute transactions in exactly the same order that you submit them, without interleaving things, then I'm ending up with a single-threaded queue that we said before, right? But if I can interleave them and have different notions of correctness, then that's okay. Then that makes our lives a lot easier. All right, so now we've got to say, how do we identify whether it's actually equivalent or not? And I'll say what we're going to talk about here is in this world, we're assuming that the database is fixed size. I mean, we have the objects all ahead of time. And we're going to assume that we have all of the operations that each transaction wants to do ahead of time. In most systems, you don't have that, right? Most systems, you don't, are not fixed size. They're not immutable, so you can't allow insert and deletes. But also, most systems don't have all the schedules of the transactions ahead of time. So that's what next class will be. How do I handle the case where transactions are submitting queries and I don't know what the next query is going to be? For this class here, we're assuming that we have things ahead of time. So we have to understand, what does it mean for transactions to have conflicting operations in their schedules? So we're going to find a conflict to occur is if there's two operations that are in both two separate transactions, and they're either trying to do something on the same object, and at least one of them is going to be a write operation. So the thing we're trying to avoid are now called anomalies. These are the problems that can occur if you're not executing things in serial ordering. So we're going to identify the anomalies that can occur so that when we start interleaving transactions, we avoid these problems, because if we have one of these problems, then we know that it's actually not going to be equivalent to a serial ordering, and therefore our schedule is not serializable. So we're going to go through the three basic ones today: read, write, write, read, and write, write. Why no read conflicts? Yeah, because who cares if you and I read the same thing? Who cares, right? There's actually two other anomalies that we're not going to talk about today, but we'll cover in upcoming weeks, called phantom reads and write skew. Phantom reads is when you do scans. If I scan a range of data, and then someone inserts something or deletes something within that range, and I do that scan again, and now the thing I saw before is gone, and now I get incorrect aggregation or whatever I'm trying to compute, that's called a phantom. Again, we'll cover that next class, how to handle that. And there's another anomaly called write skew. This one's a bit more complicated. This one we do multi-versioning. This is if two transactions are trying to update the same database at the same time, and they want to read what's in there and then update, again, like an aggregation or something else. They may end up reading the same database state, but then end up have conflicting writes. It's not exactly the same as write skew. Again, it's a bit more nuanced. We'll cover this when we talk about multi-versioning in a few more lectures. As I'm pointing out, there's more stuff here other than these three here. All right, first one is read-write conflicts. We're also called unrepeatable reads. The basic idea here is that I'm trying to read something from the database in my transaction, and then when I try to read it again in that same transaction, I get a different result. So transaction T1 starts, it reads $10 from object A. Then now T2 starts, it reads $10 from A, but then it writes back $19. Then it goes commits, and then now T1 starts again, and when it reads A, it gets back $19, right? If I was executing these transactions in serial ordering, this could not occur. The first transaction would read $10 from A. When it reads A again, if it was running all by itself in serial order, then it should see $10 again, not 19. So we have to make sure we don't have this conflict. The next one is write-read conflicts, are also called dirty reads. Right, so T1 starts, does a read on A, then it writes A back as $12, but then now T2 reads A and gets the update from that T1 made. So sees the $12 that T1 put in. So then it writes back, I don't know, $14, right? But then T1 aborts and rolls back. But T2 is already committed. Again, when you go commit, you're telling the outside world all the changes you made, they've all been applied. But again, if we were executing in serial order, this couldn't occur because T2 should not see the update, should not be able to read the update that T1 made, because T1 has not committed yet. Right? So we have to avoid this kind of conflict. So the question is, why is this a conflict? Or what's the issue?
The conflict is that the write was like +2 and not the absolute value of 14. So we're just writing +14 and the commit would have been fine.
So the statement is like, if there's high level semantics about what the read and writes actually are, would this avoid this problem? A few more slides, we'll get there, yes. But in this, assuming there's like, again, all the database knows is read and writes. So I read A, and the same on the application code that says, if my balance is more than $10, then go put $2 in or something like that, right? So like it read something from a transaction that had not committed yet, and if you're executing serial order, it should not be able to see that change. That's what we care about. Yes.
So you think another transaction should only be able to read an updated value of the first transaction committed?
Statement is, am I claiming that a transaction should not be able to read an object from the database with an updated change unless the transaction that made that change has committed? Yes. If they were executing serial ordering, yes. Yes.
What if like the transaction committed in the middle of another transaction?
The question is, what if a transaction committed in the middle of another transaction?
You first read something and then another transaction on that thing committed a write.
Yeah.
And then you read it again and you got a different value.
We just covered that. That's this. That's the first one. Oh, sorry. That's the read-write conflict. So that's exactly what you said. I read A, I get $10. This guy puts $19 in it. I read it again, I get 19. I shouldn't see that. All right. Last one is write-write conflicts. This is also called loss updates. So I have two objects now, A and B, that I care about. T1 is going to write A, put $10 in. T2 is going to start. Doesn't care about what's in A now, right? It's not reading it, just writes it. So this is called a blind write. So I'm writing into A, putting $19 in. Then now I'm going to write B and put Bob in. But then T1 comes along and it puts Alice into B. So my end state of the database in this example here is going to have $19 in A and Alice in B. And that's invalid, right? That's not, if it was true serial ordering, it would be either $10 in Alice or $19 in Bob. Right? So, we want to avoid this problem. All right, so this gets a little heavy here, but we'll go through it. I think figuring out conflict serializability is pretty straightforward. View serializability is a bit more nuanced. So basically, we want to say, all right, so now we have these schedules. We know what these conflicts are that can occur, right? Ignoring phantoms, ignoring write skew. So how can we check whether a arbitrary schedule is not going to have any of these things other than just us looking at them, trying to manually figure them out? Because that would be laborious to do and is not scalable. So there's now going to be two different notions of serializability. Remember, serializable schedule means that it's equivalent to some serial ordering of our transactions. But now there's other notions of correctness to say something's actually serializable. The first one is the most common one called conflict serializability. And that's just figuring out where you have conflicts between these transactions. There's another notion called view serializability, which is if you understand the high-level semantics of what the application actually wants to do with the data, it's sort of what he was proposing, where it may be okay that you have conflicts because in the end, it doesn't matter. So any system that's going to do transactions is going to give you conflicts, and supports serializable transactions or serializable ordering is going to do conflict serializability, even though they don't call it that. That's implicitly what they mean. View serializability is a more complicated notion because you need to actually look in the application code, or maybe even talk to the human, which is the worst thing to do, to ask them, like, what does it mean for things to be correct? There's even other notions of correctness and serializability that we're not going to cover in this class. There's a whole sort of a Venn diagram we'll cover. But these like conflict serializability is the main one. View serializability I'll show briefly because again, you'll see how to sort of handle the one case that he brought up. All right, so now we're going to say that two schedules are conflict equivalent if and only if they are going to involve the same operations on the same transactions, right? And we're going to be able to identify that the ordering of those operations on those objects will occur in the same way. So now we're going to say that a schedule is conflict serializable if it's a conflict equivalent to some serial schedule that puts the database in the same state. So me sitting up here and looking at text and being hand wavy doesn't help. So let's look how we actually compute this in the real world. So we're going to compute what's called a dependency graph. I think Wikipedia might call them precedence graph. They're all the same thing. Where now we're basically going to have a node in this graph for every single transaction that we have running in a schedule. And then we'll have an edge between those two nodes if there's an operation that is in one transaction that conflicts with another operation on another transaction, and the other operation occurs later in the schedule. So the thing we care about, if we end up with a graph that has no cycles, then we know that our graph is conflict serializable, and therefore it's equivalent to some serial ordering. If we have a cycle, then we know that it's not serializable. So we go to an example here. So T1 is going to read A, read B, and write B, and T2 is going to do the exact same thing. So in the first case here, we see a write on A that occurs before the read on A in T2. Therefore, I'll have an edge from T1 to T2 that corresponds to this conflict here, right? Likewise, I would have a write on B followed by a read on B, right? So therefore, I have an edge going the other direction. So now I know I have a cycle in my dependency graph, and therefore I know I have this thing's not conflict serializable. I'm not showing there's a write on A and a write on A. That would be another conflict, but that would just be a redundant edge between T1 and T2. And same for the write on B and the two writes on Bs. So again, the issue here is that the cycle in the graph basically is telling us there's a dependency between modifications that are being made by one transaction and the read or write operations in another transaction, and that they shouldn't be able to see those changes, or all the changes should go in one direction and not have cycles going back to the other direction. We can expand this out now for 3 transactions. So it's the same thing, we're doing reads on A and writes on A across T1, T2, T3. So we start off with the read on A that has a conflict with the write on A. Read on A in T1 has a conflict with the write on A in T3. So we have an edge from T1 to T3. Then we have this write on A to a read on A between T1 and T3 again. So we just have another edge there. Then the write on A and the write on A between T1, T2, T3, again, another edge. Now we have this write on B to a read on B between T2 and T3. So we have an edge in this direction. And then we have, again, the write on B and the read on B, the write on B and the write on B between T2 and T3, actually T2 and T1, so we have the same edge. So in this case here, because we have no cycles, we can say that this is this is equivalent to a serial execution of executing T2 followed by T1 followed by T3. Even though T1 called begin first before T2, right? The end state of the database will be equivalent to T2 actually running first, followed by T1, followed by T3. And that's okay. Right? T3 actually even commits before T1 does, right? But we're saying that T3 occurs, sort of in this logical view of the ordering transactions, occurs after T1 commits, even though physically it did not. And that's okay. Does it make sense? Pretty cool, huh? All right, so let's look at another one. So now again, we have T1 doing the read on A, write on A, read on B, and write on B. And now I'm including the application logic. Instead of just having A automatically update the database, I'm having the procedural code you would have in your application to like take A, take $10 out, and then transfer the $10 into B's account, right? And obviously you have to read the account in order to know what the value to put into it. And then now you see also in T2, I'm computing some kind of sum, which is adding up all the money that's in accounts A and B. And then I had this little return sum thing here. This is actually not valid SQL. I'm just trying to show you that after the transaction commits, you would report back whatever the sum is to whoever asked for it. So in this case here, T1 does a write on A, and that's going to have a conflict with the read on A in T2. So therefore, we have an edge from T1 to T2. But then later on, I have a read on B followed by the write on B, so T2 to T1. So then I have another edge going the other direction. So at this point here, we know that it's not conflict serializable because we have a cycle. But can we modify the application logic in T2 where we don't actually care about what the values actually are and then still produce the same correct result, even though we have a conflict or have a cycle in our graph? So if I change from just getting the total amount that I have in my bank accounts to just counting the number of bank accounts that have $0 or more, and then the only thing I care about is reporting that count actually than the actual total amount that's in the bank accounts, then this is actually would be correct if I order them in this way. Right? So again, this is going back to that same point. If you understand what the application actually cares about, some higher level semantics where for this application or this transaction, I don't care about the total amount, I just care about counting the number of accounts. Then if you have an interleaving like this, it's still considered correct. So this is what view serializability is. It's a broader, more relaxed notion of correctness than conflict serializability, but it requires you to understand what the hell the application actually wants. And again, if you either have to examine application code, that's a nightmare, or you got to talk to a human and ask them what they actually mean, and that's the worst of the worst, right? Because people don't know what the hell they're talking about. So that's why no system can actually do this. Again, so rather than going through the more formal semantics, let's look at another example. So here, I have two transactions, T2, T3, T1, T2, T3. So T1 is going to read on A and then write on A, and then T2 and T3 are just doing, again, blind writes on A. It doesn't read with the values, just overwrites whatever is in there. So if I go through and generate my dependency graph using what we talked about before, right, you end up seeing that it sort of looks like this, and we clearly have a cycle between T1 and T2. So in this case here, this is not conflict serializable because, again, there's a dependency between T2. Right? T1 is reading A, T2 is then writing it, and then T1 is overwriting it again. But if you look at the transaction, who cares actually what happens at the while the transactions are running? In this schedule here, the only thing I care about is that T3 writes whatever was in A last. It does that blind write. So in this example here, this ordering is not conflict serializable, but it is actually view serializable because it's equivalent to a serial ordering like this. Where I don't care that T2 did overwrote something on A, and then T1 overwrote that. That wouldn't have happened if I was doing serial ordering. But if my end state of the database is the only thing I care about is that A is written last by T3, then that's all I care about. So the main takeaway from all this is that view serializability is going to allow for slightly more schedules than you would have a conflict serializability. But because you have to understand what the application actually wants to do with the data and what does it mean for things to be correct or consistent, then you can't do this. So that means that if we're going to use conflict serializability as the sort of the standard in which we determine whether a ordering is correct or not, there may be some cases where we could have more parallel interleavings of our transactions, but we can't because we just don't know what is actually going on up above in the application stack. The question is, why can't I expand conflict serializability in my implementation of the data system to allow for this? Because in most systems, you don't have the transactions all ahead of time. So it would be sort of like this. It would be, I would see like T1 would start, and then T2 arrives, wants to start something, and then T3 later arrives, wants to start something, right? And I don't know in the case of like T3, is it going to now do more things after that write on A? Some systems you can do that, right? And so in the case of the blind write one, sometimes you could get away with this, but my example of like, if I'm just summing things up counting things rather than summing them, I may not be able to do that. So we're getting ahead of ourselves. So Amazon DB, there was a system called Fauna that went bankrupt this year. There's some systems that do what called deterministic scheduling, where in the case of Amazon DB, your application starts a transaction, it does a bunch of reads and writes, but doesn't actually apply any of the changes to the database. And then when you go commit, then it actually goes back and replays the transaction and sees whether it gets the same results as it did when it sort of ran in pretend mode. And if it does, then it's going to allow to commit. And now if you have your schedule, now you can reorder things and do stuff like this. The same is it like a copy and write approach? Not even that. Just like I run it, but don't apply any changes without making a copy, and then just run it again and see whether I get the same result. If yes, then I know I didn't have any conflicts. The question is, can you have rule-based serializability? What do you mean by rule-based?
If you see transactions like these, even though that it is cyclic graph, you know that these transactions tend to be view serializable. So even though you don't have transparency into the application, or just from logic, you know that such things are fine.
Yeah, transactions are so. The statement is, could I programmatically tell the data system it's okay for me to have certain interleavings? Yes. No system actually supports that as far as I know. You do this at a higher level at the application level. So you would do this. Let me give an example. So there's higher level notions of transactions. One would be like, say I'm trying to sell tickets to Taylor Swift concert. And actually the Taylor Swift concert, was it last year? Whatever, the latest tour, the database crashed because they didn't do any of this, right? But the way, because everyone's trying to update the same database and try to buy seats at the same time, so it crashed. So the way to handle this would be, if I know I have like East Coast people and West Coast people, and I don't have to communicate between each one, because that's like, I got to go across the country and that's slow. How do I allow them to update things at the same time? You can do what's called escrow transactions. You can say, I'd say I'm trying to sell, sell items. Like I'm trying to sell Taylor Swift tickets, and ignore seats because that's hard, right? But say I have a fixed number of seats. How do I make sure that I don't sell more than I actually do have? So you just basically do what's called escrow transactions. You say, all right, East Coast, you get 50 seats. West Coast gets 50 seats, and only coordinate when you run out and need to get the next 50 seats. So there's high level things you can do to handle all these cases, but no system supports that natively. If you start doing stored procedures where I have procedural code like a function that has all the transaction log directly inside the database system, then you can start doing some of these tricks. But no database system, as far as I know, looks inside the program logic within the stored procedure to figure out what the interleaving should be. All right. Let me just show one last thing before we go. I know we're over time. So the way to think about this scheduling stuff is think of like, there's this giant universe of all the possible schedules you could have for a set of transactions. And there's a very small region in the middle that corresponds to the serial orderings, right? We're just executing the transactions one after another. And then around that, there's a slightly larger region of conflict serializable schedules where you do allow interleavings, and then they're equivalent to a serial ordering. And around that, it's going to be view serializable, because anything that's view serializable, anything that's a serial ordering is by definition has to be view serializable. So around that, you have a larger region, and it's hard to figure out how to get into that larger region. And we'll see next class, there's other regions that span in other directions that can be all schedules, and some may be serializable, some may not be, right? This is awesome stuff, and we'll cover more of this in the next couple classes. All right, let me just finish up and say durability. We talked about this already before, how to make sure that if we crash and we come back and we see all our changes or roll back any changes, and logging and shadow paging is how we're going to do that, right? All right, so to finish up. This stuff is awesome. Hopefully, I'm not getting too excited, but this is super hard to do. This is why all those NoSQL systems that came out, I don't know, 2010s, like the Mongos and the Cassandras, all those people didn't do transactions. They told everyone transactions were a bad idea because it's really hard to do and really hard to get correct. And now people realize, oh, transactions are a really important idea, really good, because you don't want your JavaScript programmer writing random and coming up with invalid state, right? I mean, we'll talk about vector clocks. Like if you have to have people reason about vector clocks, that's terrible. That's like they can't do that. So basically, there was this big movement in the 2000s. Everyone was saying, "Oh, transactions are a great idea. We should do that." Sorry, transactions are a bad idea. We're not going to do that. We're not going to support SQL. We're not going to support the relational model. And then they've all come back around basically and now support all these things. Can anybody name the one company that was sort of inadvertently pushing this idea that transactions are a bad idea? There was one company that was at the forefront of all this in the 2000s. Starts with a G. Google. Google had this system called Bigtable. In the paper, they said, we're not doing transactions, we're not doing SQL, we're not doing relational model. Everybody saw that and said, oh, Google's making a ton of money. They must know what's going on. Let's do the same thing. Let's not do transactions. And then they've all come back around and said, oh, yeah, transactions are a good idea now. Google figured this out too with Spanner. So this is the Spanner paper came in 2012. So meanwhile, while everyone was saying we're not going to do transactions, internally, Google's like, oh, we need transactions. And they eventually added it. And if you go read this paper, there's this great little blurb right here. Oh, it's disappointing. All right. There's this great little blurb. Let me just show it without the animations. Where they basically admit, oh yeah, not having transactions was a bad idea because you're better off having your rando programmers, aka JavaScript programmers, not worry about correctness issues. It's this blurb here, right? They have this great line. We believe it's better to have application programmers, JavaScript programmers, deal with performance problems due to overuse of transactions as the bottlenecks arise, rather than coding around the lack of transactions. They're basically saying, get like Jeff Dean and really smart people, and you pay them a lot of money, make your transactional data system work really, really well, and that way the unwashed masses can take advantage of them and not spend the time reasoning about eventual consistency and other correctness issues. Okay? All right. So next class, we'll talk about how we actually do this at runtime with using two-phase locking, and we'll talk about these sort of more relaxed notions of serializability. Actually, not even call that. Relaxed notions of correctness with isolation levels. And then we'll do some demos and see where things go wrong. Okay? I don't know if it's going to work, but go for it. Try it.
Maintain but never strain flow with the grain. Get the fortune, motherfuck the fame. Maintain but never strain flow with the grain.